session of morning event celebrating the 17th anniversary of DAM. I have the pleasure to announce a conference of Moritz, how to introduce his Spacetime locally natured for general relativity shock wave.
No, thank you very much for the introduction. I'm very happy to give this talk in honor of Dan's birthday. As a postdoc here, I always enjoy talking with Dan, and I hope we can continue that very long into the future. So I'm going to talk about a subject which is slightly remote from the main subject of the conference, but I hope you will enjoy the talk anyways, at least to some extent. So it's about general relativity, so gravity is not neglected in this talk, and shock waves. And another connection to the main subject of the conference is that it's joint work with Blake Temple down here. Okay, so let me begin by giving a mini talk of the subject within the talk before I start the actual talk. So at the heart of general relativity is the Einstein equation, so this guy. So the left-hand side is space-time curvature, coupled to the energy-momentum tensor that describes the matter content of space-time. That's the heart of the theory. That's essentially it's a system of nonlinear wave equations for the metric tensor G. So the metric tensor, just think of this as a matrix, pointwise a matrix, which gives rise to a sort of scalar product. And I always put these indices mu, nu, and so on whenever something is a tensor in the talk. Okay. Now, the right-hand side is always divergence-free, so it satisfies this conservation law. So shock waves can live in the right-hand side of the Einstein equation. So shock wave is then a discontinuity in T, in the energy-momentum tensor. So if that thing is discontinuous and the curvature is discontinuous, so what's the effect of the discontinuity of the shock on the metric tensor, the fundamental object of geometry? So to be a little bit more specific about this, the existence theory for shock waves in general relativity only gives you a Lipschitz continuous metric tensor, no smoother. And this regularity is so low that these locally inertial coordinates might not exist. And I will define them later on, but what's intriguing about it is that you need these coordinates as a bridge between general relativity and Newtonian physics. So in these coordinates, it becomes clear how relativistic equation of physics reduce to Newtonian physics. So if you lose them, new terms could arise in this limit, and who knows, I mean, it could be funny, some funny mathematics, maybe it's some physical effect, it's not clear, but this question arises. But before you ask the question about new physical effects here, you need to worry about coordinate effects, because this existence theory, you first pick a coordinate system and then you solve the equations. So maybe this low regularity is a coordinate effect. So the central question of this talk is, can you raise the Lipschitz regularity of the metric, so we assume a given solution, so Lipschitz C01, by one level to C11 by a coordinate transformation? So we start with one discontinuous derivative in the old coordinates, and we want to get another derivative, so that second derivatives are discontinuous in the new coordinate system. Okay, and this regularity is then sufficient to construct locally inertial frames. Okay, so here's the results so far. So there's one old result from Israel in '66. So across a single shock wave, you can always smooth the metric, you get local inertial frames back, and everything is good. For shockwave interactions, the only result I know of, at least, it's the one by myself and Blake Temple. And across the point of what we call pure shockwave interaction, you can always smooth the metric tensor to C11, as long as it's spacetime is spherically symmetric. So by pure shockwave interaction, it just means interaction where two shock waves run together and two shock waves go out, so no refraction waves or anything is involved. Okay, beyond these results, the problem is completely open. And so lately we started wondering whether there's maybe a more abstract mechanism behind these results that gives you the smoothing. And in particular, we don't want to put in information about the shock surfaces so that we can address solutions generated by a glimpse scheme. When we got this following intermediate theorem, so if we assume Lipschitz continuous metric and the curvature of this guy is bounded, then you can smooth this metric to C11 if and only if the curvature of the singular part of the metric is 0. So I'll make sense of this later on, so you can define this curvature of the shock discontinuities in this very general setting. And if this vanishes, you can smooth the metric. So it's kind of a very geometric picture on the problem. And that's why we're excited about it, because it opens a whole new window to think about this problem. And what's also nice is it's very general, it's in n dimensions, and in particular it also applies to solutions generated by the Glimm scheme. Okay, so that was a mini talk. It's in the talk, and it took much longer than I expected. So let me first introduce relativity and shockwaves and relativity a little bit. So classical mechanics, that's theory invariant under Lorentz transformations, and therefore the speed of light depends on the motion of the light source with respect to the observer. And that's violating experiments and observations, and so you need transformation which maintains the constant speed of light. That's what Lorentz transformation do, and the mechanics that's invariant under Lorentz transformation is called special relativity. Both of these theories have the feature that they're invariant for transformations between observers in constant relative motion. So the constant motion is here the key word, and that's a shortcoming. So what happens when you want to transform to an accelerated observer? So it's not incorporated in these theories, not intrinsically. So Einstein didn't like that, so he wanted to find a theory that's invariant under these transformation accelerated observers, and that's general relativity. Okay, so that's a theory that incorporates transformations to accelerated observers. Now, if you do that, your space, your geometry becomes a Lorentz metric. So that's quite easy to guess. So if you transform a Lorentz Euclidean metric in R3, it's a general coordinate transformation, so Jacobian transforms that, you won't maintain this diagonal form of the metric. You get some general metric, the general matrix that gives rise to to Riemannian metric. But here we have to do it with Minkowski metric, so you get the -1 to count for the time. And making a general transformation, you end up with some general metric of the same signature. That's what you call a Lorentz metric. Okay, so general relativity comes equipped with a space-time, some curved Lorentz manifold. Okay, but what's now really interesting physically about this theory is that it must be a theory of gravity. And that's if you just picture yourself in an elevator. Let's say you're a little bit confused, you don't know what's going on in this thing. You might conclude that the gravity increases. And so you might conclude that acceleration, well, if you know a bit more, you might conclude acceleration and gravity are the same thing. If you take this as an incoming assumption, you see that the theory of accelerations here we have, general relativity, must also explain gravity. And from this experiment, you also see that gravity is no force. It's force-free motion along geodesic lines. Because if you picture a particle at rest in Minkowski space, so flat space, and now you're in the elevator, you're accelerating, you feel the gravitational field, and you see this particle falling with respect to this gravitational field you feel. However, it's because it's at rest in Minkowski space, it's also moving on geodesic lines. So educated guess, gravity, particle on the gravitational field follows the geodesic line. Okay, that's the meaning. That's why gravity is no force anymore. So the source of gravity in classical mechanics is matter. So how does the matter relate to the space-time geometry? That took Einstein 10 years to figure it out. It's done with these Einstein equations. So you can also use the insight from the gravitational field. You look at geodesic deviation, compare it with classical tidal forces. That gives you a relation between the Ricci curvature tensor and the matter content. Of course, matter must be this tensor, so it's the energy momentum tensor. The problem is this thing is not doesn't conserve energy, so you have to throw in this term, and then you get the complete Einstein equations. Okay, so that's general relativity in a nutshell. Let's look at a specific matter field interesting for shock waves. So that's matter fields for perfect fluid. So here we have the T is of this form. U is the fluid 4 velocity, so it's a tensor. We have the energy density or mass density, it's the same thing here, and the pressure. And now requiring that this thing is divergence free gives you the relativistic Euler equations. And again, you have to impose some conditions here for the equations to close, like in the classical case. So you kill one of the 4 fluid components, and if only 3 left, you kick out the pressure, and so the equation close. So to describe a self-gravitating fluid in general relativity, you have to couple the Einstein equation with the fluid source, so this guy, to the conservation law for fluid. And now this coupled system describes a self-gravitating fluid. And shock waves can form here, and you can also solve this equation by a Glimm scheme. So there exists, so you can generate shock solutions by Glimm scheme, at least in spherical symmetry, so you need to reduce to 1 dimensions. And that was done in 2004 by Temple and Graw. And here's a theorem. So I don't really want to look at the theorem, I just want to explain the settings. So you assume the spherical symmetry, that means that your metric can be given in this form. You just have these two free functions, A and B. And your space-time, so the space looks a little bit like an onion, so you have spheres of symmetry, and the only non-trivial dependence is in the radial part and in the time. And so this incorporates many physical situations. Well, and so you get a solution in the spirit of Glimm. But the important part for the talk is that the metric components turn out to be only Lipschitz continuous, no smoother. And that's very easy to understand, which we see in this talk, on this slide. So if you compute the Einstein equation for this metric here, so just look at the first Einstein equation, it reads like this. Now the right-hand side is discontinuous. The discontinuity must be compensated for by this derivative, because this is not differentiated. And so the solution can be at best Lipschitz continuous. And it actually turns out it is Lipschitz continuous. So that's where the low regularity comes from. And this smells a lot like a coordinate effect. And so the central question of the talk, just to repeat it, can you raise a metric regularity from C01 to C11 by C11 coordinate transformation? So that's new information here. So we need to look at this class of transformations. It doesn't work out for C2. So we have to restrict to larger the class of coordinate transformation. And in this pretty much the largest class, more or less, under which the Einstein equations make sense. So just say, if you go below that, you might end up with an inconsistent system. So anyway, so that's the question. Now the question of physical implications, let me just say 2 or 3 words about that. So first of all, local inertial frames, this coordinate system which I mentioned in the title. So that's by this we mean a coordinate system which is focused at some point P, and it has a property that at this point P, the center, the metric is just a flat Minkowski metric, so it's this diagonal matrix, essentially. First derivatives vanish, and second derivatives should be bounded. And this implies that G must be C11 regular at this point. And now what's important is that you can use the Lipschitz estimate for the first order derivative and derive this type of equation. Now if you plug this in relativistic equations, then if the point Q approaches the point P or at the center, then delta goes to 0, so that's just a Lipschitz bound, which you call coordinate distance. So that thing goes to 0. And in this fashion, relativistic equation reduced to Newtonian physics. Now, of course, if you cannot smooth the metric to C11, then you lose this property here, and you get some constant which bounds that from below. And this constant will survive the Newtonian limit, and you might get new terms in this limit. So I skip these slides that lie underneath this, or that explain that in more detail. So the question is, can you remove these terms? And if not, we talk about this regularity singularity. And you can't scale them down or remove them by smooth coordinate transformations. Okay, so that's kind of the physical motivations. If you can't smooth the metric, something funny happens, which might be physical. But we first have to figure out, can you smooth the metric by coordinate transformation? Okay, so now that's what I want to talk about for the rest of the talk. So, as I mentioned before, across a single shock wave, you can always smooth the metric. That's the old result by Israel. It's a rather famous paper, almost 2,000 citations. And so famous that I guess I can just skip it to buy some time. But the problem with this method is that he picks these specific coordinates. And in these coordinates he sees, okay, everything's nice and smooth. You can just read it off from the Einstein equations. The problem is these coordinates are aligned with the shock surface. So if you have 2 shock surfaces, it simply doesn't work out. So the method fails in the very first step. So if you want to address shock wave interactions, then you have to start from zero and build a new method. Okay, so that's what the last 5 minutes are. It's 5 more minutes or something like that? 10? Okay, perfect. Okay, so now that's the main result I want to talk about. So how to smooth the metric across a shockwave interaction. So the interaction we look at is of this form. So we have two shockwaves running together, interacting, and two shockwaves coming out. So we label them by these gammas. We parameterize them this way, so we can do that if the shockwaves are slower than the speed of light. We assume the setting of the Grau-Temple existence theory. So we have only these two metric components A and B. And so we are in the spherically symmetric spacetime, so this restricted setting. Okay, and then we need a bunch of regularity assumptions. So essentially just that the metric is nice and smooth away from the shocks. The energy momentum tensor is smooth and so on. We assume a given solution. And here we need a little bit more smoothness along the shock waves. And that's our setting. Okay, now that's again the main theorem. So for these type of shockwave interactions, you can find a coordinate system, coordinate transformation, which is smooth symmetric to C11 regularity, if and only if the Rancuni-Gonier condition, so they take on this form in relativity, if the Rancuni-Gonier condition hold across each of the shock curves. Okay? So the Rancuni-Gonier condition are the driving force for the smoothing here in this two-dimensional setting. Okay, and because I really like the proof, I'm super ambitious here, so I like to talk a little bit about the proof. So the idea is you construct the Jacobian of a coordinate transformation that does the smoothing. And there are 3 steps. So I'll just explain it for a single shock curve to be not so technical. So the first step is you derive a condition the Jacobian has to satisfy on the shock so that it can smooth the metric in the first place. First step. Second step is find functions that take on this condition as your prospective Jacobians in the second step. And you must define them in the whole neighborhood of the shock. Okay, in the third step, make sure that you can integrate the Jacobians to coordinates. Okay, so let's look at these smoothing conditions. So that's how the metric transforms on a coordinate transformation. So that's just the matrix transformation law, change of basis for a matrix. Okay, so we assume this metric is C1, this is Lipschitz, so that's the Jacobian of the coordinate transformation. And now we differentiate the whole thing and take the jump, and then we end up with this equation. So that's the smoothing condition. What's interesting is if we consider the Jacobian as a free parameter, then this is a linear equation for the jumps and the derivatives of the Jacobian, and we can solve it. So this is the solution. So we see the Jacobian on the shock enters again as a free parameter, and we get the jumps in the metric derivatives here, and these are fixed. Okay, so that's an explicit solution of the smoothing condition. That's step 1. Step 2, we must make sure we find functions that pick up these values when we take the derivatives and the jumps on the shocks. That's step 2. So that's done here in this ansatz. So this is chosen to pick up the R derivatives of these values we just saw. This absolute value function locates the shock position. So when it's 0, we're on the shock. If you take a derivative of this thing, it becomes discontinuous. That doesn't appear. This is a free function. It's C2 or whatever, C infinity. It doesn't, actually C1. It doesn't interact with the smoothing condition, so we can pick anything we want. And this ansatz satisfies the smoothing condition if and only if the Rancuni-Gonier condition holds. So, so that's actually quite surprising, but I have no time to really get into the details here, so let me skip that. So now let's talk about step 3. So to make sure that these ansatz we just saw is integrable to coordinates, we need to solve this PDE, so that the derivatives commute with the index here, so second order derivatives of the coordinate should commute. And so we substitute the Jacobian ansatz, so this guy, which we had from before, in this equation, and we need to use these C1 functions, the free functions, to solve this equation. So we end up with this type of equation. The left-hand side is nice, it's pretty much hyperbolic, it's linear, it's great. The right-hand side is a mean guy because it's a non-local term that stems from these fixed guys which are rigid on the shocks. So we get a non-local linear equation, which is quite annoying. However, for the single shock case, it's quite easy to handle because we just prescribe initial data along the shock curve, and then this thing becomes a given source term. Not a big deal to handle that, standard hyperbolic theory. And we can solve it and get a Lipschitz solution. Great. Well, actually, it's a big problem because the Lipschitz is not good enough. It's a huge problem because we need C1. Otherwise, the free functions would enter the smoothing condition and they would destroy the whole construction. So the only thing that can help us now is the miracle in the form of this miracle lemma. And that comes from the Rancunier-Gonio conditions. So if you just compute the jump of this equation, you can compute around and you see that the jumps of these guys give you exactly the Rancunier-Gonio condition in terms of the metric, for you use Einstein's equation to translate that and so on. And so you know they vanish, and therefore you have no jump transversal to the shock, and then you have regularity along the shock and so on, and that's good enough to conclude with C1 regularity. Okay, and this concludes the construction. Okay, now I have like 1 or 2 more minutes. So, so for the shock interacting case, you do the same thing on the upper part of the interaction. You modify the steps. So the Jacobian looks more complicated because you have to sum over both shocks simultaneously, so you get mixed terms. Step 3, you cannot prescribe initial data along the shock because you have 2 shocks, so you have to use an iteration scheme, and it's quite technical, but everything converges after a lot of pages and works out. So you get the Jacobian on the upper side. Do the same for the lower side, get a new Jacobian. And now what you have to do is you match them in a way that you don't mess up the metric regularity. So you get a lot of conditions, and again they look overdetermined. But the Rancunier-Gonio conditions come in to save the day again. And that finishes the proof for the smoothing of the metric here. Okay, so I have to skip all this, of course. Now, one more minute? 2 minutes? Okay, 3 minutes, perfect. Yeah. Oh yeah, actually it was, okay, perfect. So now, so that was the result about the explicit shocks running together. Now let's look at the abstract mechanism behind the shock smoothing. So there's this geometric picture, including the Riemann curvature tensor, and we had this theorem. So here we look at the very general setting, so we forget about the metric, we look at the metric connection. That's a potential you throw in to get covariant derivatives. That goes like a metric derivative, that guy. So metric in C01 is like this guy in L infinity. And to control everything, the whole analysis, we make this regularity assumption that the Riemann curvature tensor is also in L infinity, same regularity, even though this guy goes like a derivative of gamma. But not all derivatives appear, and you can have cancellation and so on, so that makes sense. And so that's our theorem, which I mentioned in the beginning. So you can smooth the connection to C01, to Lipschitz continuity. So the metric goes into C11, if and only if there exists a Lipschitz continuous tensor such that the space-time connection minus this tensor is Riemann flat. So the Riemann curvature tensor, whatever that is, actually this guy here, vanishes of this guy. And if that's the case, then you can smooth the connection and you get locally inertial framebacks and everything. Now what's really interesting about is that this gives you a lot of new pictures, because this continuous thing, if you subtract something continuous from something discontinuous, it will still be discontinuous. And therefore, doing this doesn't change the discontinuous character of the singular part of the shock. And so you could use this now to define the curvature of the singular part being either 0 or non-zero. So it's only digital information, but still it's information. And you can also write this as a variation problem by minimizing over all these Lipschitz tensors. And then you have to take a square of this, you have to introduce some background metric and so on, but you can do it, and maybe that is interesting. Or you can just think about, can you extend the singular part of the connection into flat space? Can you embed it into flat space in the spirit of the famous Nash embedding theorem? So that's maybe another point of view you can have on the problem. Anyways, so we're very excited about this theorem, because we kind of believe that we will be able to solve, or at least understand, much more general context behind the smoothing of these singular structures at shocks with the help of the theorem. And maybe one more minute. I guess it's my JT new here. Okay. Let me skip all the proof stuff here. The interesting part from this proof is you have to mollify some things, and you have to handle a non-zero curvature. And so we thought maybe we can do that to smooth the coordinates by this construction. It probably doesn't make any sense what I'm saying here, but anyway, so in 2 dimensions you can use a modified construction to get locally inertial frames back. So you can prove that you can smooth this to Lipschitz continuity, but only at the center point, not in the neighborhood. But you can do that in general here. That's very surprising, but only in 2 dimensions. It doesn't work in n dimensions like the original theorem. And you can extend that to the physical case of spherically symmetric spacetime, so that solves at least one problem partially. And so to summarize, you can smooth some special cases in a neighborhood. You can get local inertial frames back in every spherically symmetric spacetime and remove these weird terms in these spacetimes. But beyond that, everything is unknown. And then, most important slide, so happy birthday, Dan. And thank you for listening. And sorry for the high speed and the acceleration during the talk, but kind of fits to the subject.
And the most exciting would be to find the case where it doesn't work.
That would be interesting. Actually, we thought at some point we had that. Once gave a talk about that. It turned out to be wrong. But actually, I wouldn't say that this necessarily is the most exciting case. It's also, I mean, just to see how all the Ronconi-Agonia condition interact with general relativity. It's so beautiful, and at so many steps in the construction, this thing breaks down. Just to see that it doesn't break down, it's so fascinating. Also, that all this geometry sits behind this analysis problem and this regularity problem for Glimm scheme. I think it's so fascinating that I think either side is interesting. But of course, if something is new and funny, it's always more intriguing.
But C11, it's actually what is generated by the material shock. Right? If you do material shock, it directly generates C11 in the matter. It's natural.
Well, I mean, for the Einstein equation, because it's second-order equation, you would expect that. But in these coordinates, and because you have this constraint equation on the initial data surface, you run into these problems with the Lipschitz regularity, because you get first-order terms and so on. But yeah, so C11 would be more natural, but there's no existence theory that gives you anything in that direction. Yeah.
So in practice, you don't know where the shock is.
Yeah, if the solution generated by a Glimm scheme, you have no idea.
Know,
yeah.
So you cannot do this construction.
Yeah. I mean, with these solutions, no chance. That's why we look at this abstract setting, this geometric setting, because you really want to understand what's going on with the mechanism. And the construction I showed in the beginning, you can construct solutions by matching together spacetimes. That's Schwarzschild already did that. So it's like pretty common in relativity. And they, of course, you know where the shock lies. You can follow it, and then you could do this construction. But for these general existence theory, it doesn't help at all. Plus, you have the problem if in a Glimm scheme, and all these points of interaction lie very close together, you always have to zoom in around the point. So maybe you can smooth the metric in theory, but you lose all information about the rest of your coordinate neighborhood, and so that's very unsatisfying. That's another shortcoming of this first method.
Moritz, I have a curiosity. What implication have these theorems for the general relativity theory?
Could you repeat that?
What implication have your theorems in the general relativity theory?
Oh, well, I mean, the thing is, when you get for the shocks this singular structure of losing local inertial frames potentially, and if you cannot smooth the metric, you don't get these local inertial frames, and then you would get a different Newtonian limit. And this could give you some scattering effects in like just of a particle following a geodesic line, or in gravitational radiation. So you could see something funny there. I mean, I don't want to claim this is physical, but at least something would be different if that fails. But if you get these coordinate systems back, then and if you get a constructive method, then you know what is your bridge back to classical mechanics when you look at shockwave interactions and at solutions generated by Glimm scheme. So it's always nice when you know how to connect general relativity with Newtonian physics. So either outcome has some meaning for physics, and it's quite fundamental. Yeah. So that answers the question? Okay.
Any comments, questions? Okay, thank you, Moritz.
Thank you.